Hello dear viewers, this is Dr. Aisha Nazuk here. Today we are going to start chapter number 5 of Gujarati Importer book. So if you have learned it first time on this video, let me give a quick introduction that this channel Hub deals in lecturing on statistics, on probability theory, and then econometrics, help on statistical software, and then some useful videos like how to download books. Then we have videos on positive thinking, and one playlist is on comedy and humor genre as well. So welcome to our channel and thank you for clicking on this video. I really hope that you are going to learn some basic concepts and useful concepts of econometrics by watching this video. So if you want to download this book, Gujarati and Porter are the author names. You can easily download these books from the Genesis library. I have also made a video on how to download books from the Genesis library, but just for a moment let me show you a very quick and easy layout of the Genesis library. Currently I don't have access to internet, so otherwise this would have opened. So this URL gen.lib.rus.ec, this can easily land you to the Genesis library. As I said that I have a complete video on how to download books from the Genesis library, so please watch that. So we are going to start the concepts of two variable regression, and how to do interval estimation and hypothesis testing of regression betas. By the way, contents of this video lecture will be best understood if you watch the earlier videos in this playlist. As I said, this is chapter number 5, so this is building on the concepts of chapter number 1 to 4 of Gujarati and Porter book. I'll shortly also show the list of topics, or a basic idea of what is my expectations from the viewers, that they must be well versed in those topics. So if you are relying on this channel to learn the concepts, please watch the earlier videos in this playlist and then come and watch this video. However, if you already have basic concepts clear, like what are confidence intervals, how we calculate the standard errors of regression betas, how we compute them, and then you can easily start watching the video and you can easily learn from this video lecture. So before I start the lecture, just a humble request that please subscribe to this channel. My contact details are also mentioned here. I'm very active on Facebook as well, so if you want to get connected on Facebook, we can have regular query sessions. You want to get some data set, you want to discuss something relevant to econometrics or statistics, you are more than welcome to get connected with me. I am, as I said, a faculty member at a university in Pakistan, Nast University. So welcome again to the channel and let's start the lecture. So what are my expectations from the students, or what are the prerequisites before you cover this video lecture, is that you must be well versed with the concepts of probability, what is probability distribution, what is meant by a type 1 and type 2 error, what are level of significance, and so on. So these are some of the concepts that if you can revise these concepts, then you can easily understand. Some of these concepts are already covered in my probability theory playlist and introduction to statistics playlist, while a couple of these may be missing in those playlists as well. So if you wish, or if you request, we can have a featured video or a video on demand where we can make more videos relevant to these concepts. Anyhow, so these are my expectations. So let's start the discussion, or the chapter number 5. Refer to the video number 7. In that video, let me show you a quick excerpt of that video, and then I'll talk about the starting example that I'm starting here. So let's go to video number 7. As this video is of course made by me, so I have the backup. This is the video number 7. You can see that we have data on hourly wages and years of schooling. So this we run regression where we regress wages on years of schooling to see how wages depend upon years of schooling or education. So let's say that we want to run this regression and we want to know the values of slope and intercept. So if you go and watch this complete video, which I am telling you that this is video number 7, you can easily verify that the slope coefficient was 0.7241. So coming back, this is what I have written, that suppose I want to regress wages on years of education and slope coefficient is 0.7240, then what does that mean? As you know that the standard interpretation of the slope coefficient is that for a 1 unit change in the independent variable, the expected change in the dependent variable is slope. So here we are going to say that if there is 1 year increase in schooling, then the expected increase in wages is 0.7240 units. Now remember that whenever we are given a data at hand, it's always data from a random sample. So that means that whatever the value of slope we are getting is based on what type of sample we had. Had we relied on any other random sample, the result for slope would have been different. So how can we say that the sample results that we have calculated are actually representative of the reality? In other words, how reliable is the estimate of slope that we have just calculated? So in statistics, the reliability of a point estimator or an estimator that is coming out of a sample, it's measured by its standard error. So before we study the idea of confidence interval, you must know the difference between standard deviation and standard error, which I have abbreviated here as SD and SE. So SD is standard deviation and SE is standard error. There's a very minor difference between these two. It's actually that if we calculate the standard deviation, it's for a random variable, whereas standard deviation of a point estimator is called standard error. So basically standard error is a special type of standard deviation, right? Standard deviation of a point estimator or anything that is calculated from a random sample, that is called standard error. So next we will discuss the concept and an example of calculating the confidence interval so that we can comment how reliable is our point estimator. Okay, so let's start. We were saying that I'm going to cover the concept of confidence interval. Okay, so what is meant by confidence interval? As we said that if we rely on a random sample, the point estimate that we develop will also be something which is dependent on sample, so it will be random. So suppose that instead of just a point estimator, we want to develop a confidence interval or a range of values within which we can expect the population slope to be contained with, let's say, a certain probability, which could be 95% or 99% or even 90%. So let's say if we focus on 95% probability, then the resultant confidence interval that we are going to shortly learn how to make will include the value of the population slope with a probability of 0.95, or in percentage terms 95%. So keep in mind, whenever we talk about confidence interval, it always have a probability statement attached with it. So if I write this equation PR of this entire thing or this range, this means that the probability of the range that I am going to make will be equal to 0.95. And how will I make this range? Suppose I want to make this range or interval for the slope. So I will have the point estimate of slope from the random sample, which we just obtained, equal to 0.7240 in the current example. So I'll use the point estimate, then I'll add and subtract a second term, which you can see that it has standard error as well as z-score attached with it. So standard error, I shortly discuss that the standard error is the standard deviation of the point estimate. So here we are talking about slope, so standard error will be the standard deviation of the slope coefficient, for which I will again recommend that you watch my video on a video in which I have discussed how to calculate the standard error of regression betas. I will post the link to that video in the comment section. So you can see that this statement, it has a probability and a range, and the probability is 0.95, and how we are going to calculate, for that we will need standard error and z-score. So what is z-score? If you don't know about z-score, then I'll add a link to a useful website where you can read and have a basic idea of what is z-score, because as I said that the course of econometrics builds upon the concept that you have learned in the course of statistics. Anyhow, if you haven't taken an introductory statistics course so far, or the concept that you studied in that course need a refresher, you can revise the z-scores from the link that I will post in the comment section. So once you know the basic idea of z-score, you will also know that z follows normal distribution with mean 0 and standard deviation 1. So this z-score we are going to derive from the normal distribution. So shortly I'll be discussing one applied example of building a confidence interval and where these concepts will be further settled. Okay, so what is normal distribution? So far the concept that we have studied regarding the normal distribution, you know that it's a bell-shaped distribution, and it's a symmetric bell-shaped distribution in a manner that its mean is represented by the Greek symbol mu, whereas its standard deviation is represented by the Greek symbol sigma, and that's why I've written that there is a sort of a mantra about the sigma, or a property about the normal distribution, that if you analyze the interval mu minus sigma to mu plus sigma, if the distribution is normal, then that interval should have 68.27% of the data, and similarly mu minus 2 sigma to mu plus 2 sigma should cover 95.45%, and similarly you have the limit for 3 sigma interval as well. So almost all of the data is covered in mean minus 3 times standard deviation. So that gives you a quick way of commenting whether a data is normal or not. You simply calculate the mean of that data, standard deviation of that data, and then you build these interval, and you can verify what percentage of values fall within these sigma interval, that is the 1 sigma, 2 sigma and 3 sigma interval. Anyhow, we are not going to do that example here, but the reason for telling these ranges is that they are frequently used in the confidence interval, and once I do that example you will further understand why this information was discussed here. So as I said, for an approximately normal distribution, the data within one standard deviation accounts for 68%, within 2 standard deviation 95%, and within 3 standard deviation 99.7%. So suppose if I want to calculate 3 sigma confidence interval, what would that mean? If I calculate 3 sigma confidence interval, it would mean that I am making an interval within which the slope coefficient will have a probability to be contained 0.9973. So the benefit of this property is, even without using specifically the normal distribution table, we can easily calculate the 3 sigma, 2 sigma and 1 sigma confidence interval. So it's understood if we develop 3 sigma interval, then the probability of slope being in that interval will be 0.9973. If I calculate mu plus minus 2 sigma interval, the probability of slope in that interval will be 0.9545, and similarly we can comment on the 1 sigma limit as well. So this was the use of the information that I have just shared. Now next, when I discuss about confidence interval, by showing this data, I want you to further have an idea why we are focusing on the confidence interval and why the point estimator is not all the time useful. Suppose that we have a population on income of families and their consumption pattern. So suppose if a family is earning $100, then one such family might be consuming 78 out of it, another might be consuming 65, and so on. So what will happen when we'll be running a regression in which we'll see how consumption depends upon income. We can have different types of you can say sample. For example, one possible way of drawing a sample from this population is that we can have the consumption value 78 with 100 and then 60 with 150 and so on. That is, from the consumption column I am randomly sampling one value of the consumption against different income levels. So there can be multiple ways of doing this or selecting the sample. By the way, if you see that against income is equal to 100, we have 5 observations. So there are 5 different ways in which I can select this value. That is, one option is 78, the second is 65, third option 69, fourth option 99, and fifth option 100. So we have 5 different options. So if I count the total number of ways in which the sample could be drawn from this population, there are 320 different ways in which I can draw a random sample out of this population. Now what does that mean? That means that we can have 320 possible values of slope coefficient and similarly the intercept. Currently I am focusing on the slope, so let me emphasize on the fact that we can have 320 different values of the slope coefficient. So by this discussion we have established the fact that the confidence intervals are random because they depend upon a sample. There are 320 different ways in the last example to make a sample. So there are 320 possible confidence interval, right? Therefore, interpretation of confidence interval is relevant to the theoretical notion of repeated sampling. Now what does that mean? It means that if we have a confidence interval from a given random sample, we should interpret in a manner that we link it with the concept of repeated sampling. So how do we do it? Let's say if we have a 3 sigma confidence interval for slope as follows. I will shortly tell you how to make that interval. For now, let's say if the 3 sigma interval is this. So how we can interpret? We can interpret that if we draw k different samples from the population, then we can run k different regressions and we can have k different values of the slope coefficients. So roughly 99.73% of the regressions will produce slope value within this range. What does that mean? It means that for example, in the last example, we had 3 different ways of drawing a sample. So we can run 320 regressions, and 320 into 0.9973 is 319, because remember that we are talking about 3 sigma limits, which I just told you that the 3 sigma limit have the probability or the percentage 99.73. So out of these 320 sample, 319 sample will yield the slope value in the 3 sigma limits for slope, right? I mean, if you have the confidence interval in front of you, this is the standard way of interpreting it, rather than saying that there is this much probability that the actual slope is, or the actual population slope is within these two values. Okay, so if you want to further understand the concept of repeated sampling, you can watch my video on Monte Carlo simulation, whose link is there in the comment section. Apology, my battery is running low here, that's why you saw this on the screen. My due apology. So let's discuss further how to make confidence intervals for the intercept and the slope coefficient. So let's say for now we focus on the slope coefficient. As you will also, by now you might have learned already, or let me repeat that the sole purpose of running the regression is to comment on the relationship between the independent and dependent variable, which is portrayed by the slope coefficient rather than the intercept. So let's say we want to make the confidence interval for slope, or beta 2. So referring back to the Monte Carlo video, which if you haven't watched, you can watch. It's very handy video on how to prove that the regression betas are unbiased and their variance is minimum. So you can watch that video about the Monte Carlo simulation. We proved that if the residual term or the UR term is normally distributed, then the regression betas are also normally distributed. So that means that by now we have established that if we prove that the residuals are normal, and that we can easily prove using the normal probability plot. So if we prove that the residuals are normal or normally distributed, we can easily comment that the regression betas are also normally distributed. So if the regression betas are normally distributed, and then we can easily make the confidence interval using the z-score, which is defined as the value of slope in the sample minus the value of slope which we want to hypothesize. Actually, here you will it might be wondering that we don't have a priori expectation about the value of the slope. So why am I discussing that we have to subtract the point estimator from the expected or the a priori value of slope for which we want to test? Anyhow, the sole purpose of writing the z-score here in this form is to just give you a background idea that the z-score that we are going to use in the confidence interval is the z-score against the slope coefficient. Anyhow, we will make the interval. Let's focus on that, and we will make the interval for beta 2 or the slope, and we will learn how to interpret that. Before I proceed further on how to make the confidence interval, what you have to keep in mind is that if your random sample is very small, then you cannot use the normal distribution, and rather you will use the t distribution, right? So if the sample size is small, we are going to use the t distribution. If the sample size is large enough, we are going to use the z distribution. And by the way, if you are relying on a statistical software to do this testing or make the interval, there is no need to worry, because most of the statistical software, they are smart enough to analyze whether the data is small or large, and they are going to accordingly provide the statistical output that you can interpret. Anyhow, without going into further complexities, what I'm commenting here, that the z-score, you can see that it has a term standard error in it, in the denominator. So remember that in the z-score we also call this as a test statistic. This is a test statistic, and we want based on this test statistic we are going to make the interval. So in this test statistic, the denominator term is the standard error or the standard deviation of beta 2 hat, which we denoted by the symbol sigma. And if you don't know how to calculate this sigma, you can watch video number 5 where we have derived the standard error of the slope coefficient. So this sigma is the standard deviation of the residuals if we have population data or if we have a large sample. But if the sample size is very small, then this sigma this is approximated by the sample values. So what am I saying here, that we don't have population residual, so we don't have sigma. Instead we have sample residual, so we can calculate the standard deviation of the residual in the sample data, and if the sample size is large enough, we can declare this as z statistic, otherwise we will declare it as a t statistic. That is, if the sample size is small, the background distribution that we will be using for confidence interval will be t. If the sample size is large enough, the background distribution that we are going to use will be the z distribution or the normal distribution. So coming back, if the sample size is small, then instead of writing the z-score here, referring back to the original slide where I told you what is the standard form. You see, when I started the discussion of confidence interval, I told you that we add subtract something in the point estimate, and that something is z-score and the standard error. But if the sample size is small, instead of z-score we are going to use the t-score or the t distribution. So the t distribution is defined with the help of its crucial parameter, which is degrees of freedom. You will get to know in the coming few minutes that how we use the t distribution and what is the concept of degrees of freedom and so on. So but the point that I want to emphasize here is, irrespective of whether you use the z distribution or the t distribution, this second term is based on the standard error, right? So that means if the standard error is large enough, because t alpha by 2 or z-score or the t-score, they are fixed value. If you set the value of alpha, which is the type 1 error, if you set the value of alpha, then z-score, t-score, they become constant. So that means that what is being added or subtracted depends upon the standard error. So if standard error is large, this confidence interval will be wider, and if standard error is small, this confidence interval will be narrower. So in statistical terminology, we can say that the standard error is a measure of the precision of the sample results. So how precisely the sample results measure the true population values or the true population results depends upon the value of the standard error. So that means if standard error is a large number, that means that the sample results are not that reliable, right? There will be more of a prediction error attached with such sample results. Anyhow, so let's say that let me summarize that what we have discussed so far and how we can proceed further. Let's say that we have a random sample and we have calculated the value of slope. The sole purpose of running regression is to decide whether the independent variable significantly impacts the dependent variable. So, but the problem is the sample results, they vary from sample to sample. So for example, if you have a slope value equal to 0.7240, so how can you say that even if we had analyzed some other random sample from the same population, had the slope value been non-zero? Because if the slope value is non-zero, that means that the independent variable and the dependent variable, they are linked with each other. If the slope is zero, of course that means that the independent variable and the dependent variable, they have nothing to do with each other. So this is the reason we want to test whether in the population slope is zero or not. So our null hypothesis is that the population slope is zero. So that means our null hypothesis is that the x variable cannot explain or predict the y variable. This is our null hypothesis, whereas alternate hypothesis is that the slope is not zero. That means that the x variable can help in predicting the y variable. So suppose I want to test these two hypotheses. So how can I do that? Okay, so let's say we have the value of slope and we have calculated standard error, which you should know, especially if you are calculating it manually, then you should know what is the formula for standard error so that you can calculate it. So you can watch video number 7 if you haven't covered this example so far, and if you haven't covered how to calculate the standard error. Anyhow, so if you have the slope coefficient and its standard error, and you want to comment whether in actual population the dependent and the independent variable are linked or not. So if we are talking about the example that I just showed here, that we have data on wages and schooling, and you can see that we have 13 observations here, right? We have total 13 observations. So first of all, you can see that it's a very small sample. So we are going to use the t distribution. So 13 minus 2 is 11. So what is this 13 minus 2? This is actually the degrees of freedom of the t table. So remember that whenever we use t distribution, we need to calculate degrees of freedom. So what is degrees of freedom? Degrees of freedom is the number of sample size minus the number of unknown parameters. So here we have an unknown intercept, that is the population intercept, and an unknown slope, that is the population slope, and we want to estimate them. That is why we say that we have two unknown parameters. So 13 minus 2 is 11. So degrees of freedom is 11. So that means whenever in a regression context you want to make confidence interval and you have one dependent variable, one independent variable, then the degrees of freedom will always be n minus 2, sample size minus 2. So let's say if we assume that alpha is 5%, so what is this alpha? This is the margin of error. Remember that whenever we make some statistical calculations, we can never be 100% sure that those calculations will actually be true. Why is this case? Why is this scenario? You might be thinking that we are doing calculation, why is there some error attached to it? For this you need to understand the concept of type 1 error. What is type 1 error? It is the probability of rejecting the null hypothesis when actually it is true. That is, it is a probability that suppose the null hypothesis is that the population slope is actually 0, but you get a sample, such a sample that you don't comment that this slope is 0. That is just because of, let's say, one possible sample. It seems that the two variables are related, where in actuality or in population they are not related. So this is the probability of type 1 error. Right. So besides this example, let me tell you what is type 1 error shortly. So let's say if in a code scenario my null hypothesis is, let me write here, let's say in a code scenario my null hypothesis is that the culprit is innocent, right? Whereas my alternate is that the culprit is not innocent. Now, what will be type 1 error or what will be alpha? Type 1 error will be rejection of H naught when actually it is true. Now, what does that mean? Rejection of H naught means we are rejecting that a person is innocent, right? We are rejecting that that person is innocent, while in actual sense or while in actuality he or she is innocent. So you know that even in court cases such errors are committed. So in short, whenever we are dealing with random scenarios, then those random scenarios are prone to some errors. So this alpha is the probability of type 1 error. Now how we set the value of alpha? Generally the minimum value of alpha is 1% and the maximum allowed value of alpha is 10%. So let's say we assume that alpha is 5%. If you are considering this from an exam scenario, then the value of alpha is generally given in the exam. So you know that alpha is 5%. So how to use the t distribution? As I said that it's a small sample, so we are going to use the t distribution. We just saw that our degrees of freedom is 11. So let me zoom it a bit. So this is a screenshot of the t distribution table. Here the column heading is df, that is the degrees of freedom. So I am going to scroll down till the df is equal to 11, and then I have to focus on this second row, two tail, and I am using alpha is equal to 5%, which is 0.05. And why am I using this two tail range? Because I am making a two-sided confidence interval. That is, I want the minimum possible value of slope and the maximum possible value of slope. So that's why I am using this two tail row. Okay, so coming back, so a 95% confidence interval, because if whenever the error margin or alpha is 5%, then remaining 100 minus 5%, that is 95%, is the confidence level. So we know that using this t table that for 11 degrees of freedom the critical value of t is 2.201. So the confidence 95% confidence interval for slope will be the value of slope that we got from the random sample, and then we will add subtract this factor where we have this t term and then this within bracket, which I am going to make it in red font. So this red is the standard deviation or the standard error of the slope coefficient. So by using this formula we get these two ranges. Now the question arises is how to interpret this confidence interval. As we said that the probability that the actual slope is within these two values is 0.95, but I will shortly also refine this interpretation. For now, suppose that we don't it's not the case that we always test for whether the slope coefficient is 0 or not. Sometimes we are interested in testing other values of slope. For example, if we want to see whether the slope coefficient is equal to 0.5 or not, so we want to test this hypothesis. How can we test it? It's very easy. This time I'm going to analyze the, you see, this was my confidence interval 0.57 to 0.878. So how I'm going to decide whether I reject H0 or I accept H0. So what I'm going to see, there is a very easy decision rule that you make the confidence interval, and if the value in the H0 is covered in that interval, then you can say you should not reject H0. What does that mean? The interval that we just made, you see it doesn't cover 0.5. 0.5 is outside this range. So that means that I should reject H0 based on the interval that I have just made. So this is how you can test the hypothesis about the actual population parameter using the confidence interval. Okay. And then there is a very convenient rule of thumb. If the null hypothesis is about 0, as when we started the discussion earlier, suppose here our null hypothesis was that the population slope is 0. So if the null hypothesis is testing about the 0 value of the slope coefficient, then we have a very simple rule. If the number of degrees of freedom is 20 or more, right, and if alpha, that is the level of significance, is set at 5%, which is generally a fair value of alpha. So if we fix alpha at 5% and degrees of freedom is at least 20, then the null hypothesis that the slope of 0 can be rejected if the t value exceeds 2 in its absolute sense. So how to go about it? We will calculate the t value from the sample, and if the calculated value exceeds 2, we will reject H0. I will be shortly also discussing how to calculate the t value from the sample. For now, you can recall, let me refer back to a couple of slides earlier. You see, this is the formula for t value. So for this I need the value of slope coefficient in the random sample, that is beta 2 hat minus beta 2. What is this? This is the value for which we are testing. If the null hypothesis is that the slope is 0, then this second term beta 2 will be 0. If the null hypothesis is that the slope is equal to 0.5, then this value beta 2 will be 0.5. So whatever the value against which we are testing the hypothesis, that is being subtracted from the sample results. Then we divide by the standard error of beta 2 hat, which I have already covered, how to calculate the standard error of the slope coefficient. Okay. So coming back, that if we have a null hypothesis that the slope is 0, our degrees of freedom is at least 20, and null hypothesis the alpha is set at 0.05, then we can reject the null hypothesis if the calculated t value is greater than 2. Now you can see that our decision to reject or not to reject the null hypothesis depends a lot on what value of alpha are we setting. So that means that if we change alpha, our decision to reject or to accept the null hypothesis can change. So this is the reason that we have an alternate approach called the p-value approach. In this video I won't be covering how to calculate the p-value, but here I will only like to comment that if you run the regression in any statistical software, then the p-values are always reported. So that means that you can easily rely on the p-value. So how to rely on the p-value? First of all, you should keep in mind that the reported p-value by the statistical software is against the null of 0. Right? What does that mean? It means that, for example, if we are talking about slope, then the null is that the population slope is 0. So this p-value is reported. If that calculated p-value is less than or equal to 0.05, then you can reject the null hypothesis. And in other words, even if you don't just forget for a moment, forget about this 0.05. If suppose your calculated p-value is, let's say, 0.87, what does that mean? It means that the minimum value of alpha required to reject H naught is 0.87. So, but we know that we don't use that high value of alpha. The highest allowed value for alpha is, as I said, 10%. So even if we use the 10% benchmark, if the p-value is 10% or that is 0.10, then you can reject H naught. But at such a high value p-value, you cannot reject H naught. So that means that if the p-value is a small number, then you can reject the null hypothesis. So if you are using 5% level of significance, then if p-value is less than 5%, you can reject the null hypothesis. Anyhow, in this video lecture, we will not be covering how to manually calculate the p-value. The reason for telling you here is that if you are relying on statistical softwares to run regression, you can take benefit from the p-value approach. Even if you don't currently understand what is the concept of p-value, you can rely on the approach, the confidence interval approach that I have just taught to do the hypothesis testing. Then I will discuss what is the difference between statistical significance and practical significance. It means that sometimes the results are, statistically we decide that they are important results, but whether those results are practically important or not, that you need to decide upon. And how to decide? Let's say I try to link this discussion with the help of one applied example. Let's say we have data on marginal propensity to consume, that is, we have data on consumption and we have data on GDP or the gross domestic product, and let's say if we regress these two variables, the slope coefficient comes out to be 0.72. That means that the marginal propensity to consume is 0.72. And let's say that the 95% confidence interval for slope or the marginal propensity to consume is this, right? That is, we are regressing per capita consumption on GDP and the slope is coming out to be 0.72, whereas the 95% confidence interval is 0.7129 to 0.7306. Now let's say from a policy perspective, someone asks you that can we say that the marginal propensity to consume in this data set is equal to 0.74. And now you can see that 0.74 is not covered in this range. It's slightly outside this range. So statistically you will be saying that we cannot say that the marginal propensity to consume is 0.74 had we used the entire population data. But an economist might be saying that okay, 0.74 is not covered in this interval, but if in the given sample the slope coefficient is 0.72 or the margin propensity to consume is 0.72, then maybe we can say that 0.72 and 0.74 from a practical perspective we might be saying that these are somewhat similar. That is, what type of policy actually we are trying to what type of policy decisions we are trying to take using this data. So if my policy decision is to decide what is the value of, let's say, income multiplier, then the income multiplier is 1 over 1 minus marginal propensity to consume. Now, as an economist, I might say that if I use the value of MPC equal to 0.72 or 0.74, that doesn't make a lot of a difference, right? So practically I might be saying that okay, these results are statistically significant but practically not that significant for me. So what does that mean? It means that the testing or the statistical testing that we are doing, whether manually or in a statistical software, they can only comment whether the results are statistically significant or not. Whether the results, in other words, whatever the formulas we have used mathematically, whether they are significant results or not. But whether those results are practically significant or not, this is up to the field expert. For example, if the regression is relevant to let's say economics, then economist can best decide whether the results are practically significant. If you are analyzing some data from chemistry, then a person who is expert in that field, and that is chemistry, can comment whether the results are practically significant or not. So you need to understand the difference between statistical significance and practical significance. Next, I am going to share the hypothesis testing approach using the test of significance. By the way, it's not necessary that you apply the test of significance approach. You can simply apply the confidence interval approach as well. But the reason I'm telling how to make or how to test hypothesis using the test of significance approach as well is that some of the students or some of the viewers might find this approach relatively easier than the confidence interval. It's totally up to you which approach you are going to use. That doesn't make any difference. Okay, so what is the test of significance approach? Let's say if our null hypothesis is of this form, that slope is equal to some number. It could be any number, so I've used a general number beta 2 star. So if the null hypothesis is of this form and alternate is of this form, then we call it a two-tailed test. And then the decision rule will be that the calculated t value exceeds the table value. And how we calculate the table value, I have just discussed while I was showing the t table, that if you know the value of alpha and the degrees of freedom, you can easily calculate this value. And this simple t that is appearing here with an absolute sign, this is the t that you are going to calculate from the sample. So anyhow, if the null hypothesis is of this form, that is less than or equal to form, and the alternate is greater than form, or the second option, these two are both called the one-tailed test. And you can see that the decision rule has the same sign as the alternate hypothesis. So this is how you can decide, and let's say how we are going to use these. Before I proceed further with the concept, I will actually be discussing this hypothesis testing approach using actual numerical data, and then I'll be commenting further on these decision rules and how to use the hypothesis testing approach of test of significance method. For now, let me tell you that because here we are talking all about linear regression, and the normality assumption is very crucial. So if you haven't watched the video on how to test the assumption of normality of the residual term, you need to watch video number 9 to know how to make the plot, normal probability plot, and how to decide whether the data is normal or not. And also keep in mind that the normality assumption is not the only assumption required. There are three types of abbreviations appearing here. CNLRM is the classical normal linear regression model. OLS stands for ordinary least square, whereas CLRM is the classical linear regression model. So we use all these terms interchangeably, and there are certain assumptions attached to these models. So one of the assumptions was the normality assumption that we have covered how we can check. But there are more assumptions of the linear regression. So for now, I'm not of course going to discuss all the assumptions again and how to test whether those assumptions are met in a given data or not. Uh, we are going to cover those assumptions later in the other videos when we cover chapter number 13 of the Gujarati and Porter book. For now, what we are saying is we are only checking the normality assumption, and if the normality assumption is met, then we are saying that we are assuming that the other assumptions are also met. Later on we will learn how we can check other assumptions, what are those other assumptions, and how we can test those assumptions if we are given a data set. So let's do some practice activities that will further solidify the concepts that we have covered in this video. This is exercise number 5.5 of chapter 5. So let's say we are given a data on relevant to the stock market. So you see that here RIT is the rate of return on the ith security in a given time t, where RMT is the rate of return on the market portfolio. Actually, even if you don't have much knowledge of finance, let me tell you that this is actually linking the returns of one stock to the returns of other stocks, because portfolio is always made of different stocks. So how one stock is dependent upon the performance of entire portfolio, that could be analyzed if we run this regression. Now let's say in this model, this value which is denoted as beta I, this is known as the beta coefficient of the ith security or the ith stock. So it's a measure of market risk, right? How risky is it to invest in a particular security? We can analyze, decide by looking at this beta coefficient. So let's say on the basis of 240 monthly returns for a given time period, Fogler and Ganpati obtained the following data of IBM stock in relation to the market portfolio index. So this is all the part of the question, so you need not to worry a lot if you don't have the background knowledge of finance. The thing is how we are going to take key decisions regarding these variables. So let's say we have the regression equation, we also have the values of standard errors, and then we have these certain other values, because that sample size is 240. So the 240 minus 2 degrees of freedom is 238, and then r square as well. By the way, whenever we run regression in a statistical software, these values are always reported by that software. Anyhow, this is the question, and the first question, the first thing that you need to check is it is given that a security whose beta coefficient is greater than 1 is said to be volatile or aggressive security. In other words, that it's too risky to invest in that security. So let's say we have data on IBM. So how can we comment whether IBM is a volatile security or not? So actually you can see that we need to test whether the beta coefficient is greater than 1 or not. So I'll come back to this part B later on. For now, let's focus on part A. So what we have decided so far, that a security whose beta coefficient is greater than 1 is said to be volatile. So that means our null hypothesis will be that the slope is less than or equal to 1, where alternate will be that the slope is greater than 1. So how I have decided that I should treat this as the null hypothesis? Remember that equality signs are always embedded or put in the null hypothesis. So in the question it was given that we have to test that the slope is greater than 1, then the exact opposite of greater than 1 is less than or equal to. So that's embedded in the null hypothesis. So now you see the alternate hypothesis has a greater than sign. So I told you whenever the null hypothesis has a greater than sign, then the decision rule will be to reject H naught if T calculated is greater than T tabulated, right? How to calculate T calculated and T tabulated, I'll tell you shortly. Actually, these the images, that the three images you are seeing here are actually screenshots of an online calculator where you can calculate the value of T tabulated. Now I will share in the comment section of the URL where you can see how these values are calculated. For now, let me show you. This is a typical layout. You have to enter the values of degrees of freedom and the level of significance, and then you calculate, and T values are calculated here. So this was the screenshot that I was discussing here. Okay, so let's say even in the question we are not given any value of alpha. So we can test the hypothesis at 1%, 2% or any value. So the maximum allowed value for alpha is 0.1. So even if I test at the maximum allowed value of 0.1, the T value that is corresponding to one-tailed distribution or the one-tailed test is 1.28. So here the alternate hypothesis has a greater than sign, so it's a right-tailed test, and that online calculator is giving me the value of right tail equal to 1.28. So that means that the T value at alpha is equal to 0.1 with 238 degrees of freedom is 1.28. So this is the tabulated value, right? So now I know that this is the tabulated value. Now let's say how I can decide. If you refer back to the question, we already have the calculated value. This is the beta coefficient, and we have the standard error as well, and we are testing against a value of slope equal to, or you can say slope value 1. So in the null hypothesis the threshold value is 1. So what we are going to do, we will calculate the T calculated which is equal to beta 2 hat, that is the value of slope in the sample, which we are given that the value of slope is 1.0598. This is part of the question. So 1.0598 minus 1. Now why this one? Because the threshold value against which we are testing is 1. So the sample slope minus the threshold value divided by the standard error. Once again, as I said, standard errors are already given here. So we are going to divide by the standard error. So this is the value of T calculated. So what is our decision? The decision is we can reject H naught if the T calculated is greater than T tabulated, and we just found out that the T tabulated is 1.28 and the T calculated is 0.821, and this is not greater than 1.28. So we fail to reject H naught. That is, we are accepting the hypothesis that the slope is less than or equal to 1. What does that mean? It means that the IBM is not a volatile security or an aggressive security. So this is how we can use regression results for practical decision making. Now coming back to part B, which I have copied here. Part B of the question is the intercept coefficient significantly different from 0? If it is, what is its practical meaning? It means that first of all we need to test whether the intercept is equal to 0 or not. So this is a two-tailed test, right? Equal to 0 or not equal to 0. So the null is the intercept is 0, the alternate that the intercept is not 0. So this is a case of equal to and not equal to, which is always two-tailed. So the decision rule for a two-tailed is we reject H naught if the calculated T value exceeds the T tabulated or the calculated value is less than minus of T tabulated. So I need the value of T calculated and T tabulated. How we can calculate T tabulated? I have just shown you that the T value or the T calculator is available online on this website. I will post this this link in the comment section. So let's say if you use alpha is equal to 0.02, although you can use any other value of alpha as long as it is not exceeding 10%. So let's say if I use alpha is equal to 0.02, you can easily go and verify from that calculator that the two-tailed value is equal to 2.342. Let me show you here again. So this is 238, alpha is 0.02 and the two-tailed value is 2.34. So this is the T tabulated value 2.342. So what we have to test, we have to test whether the calculated value in the sample exceeds the tabulated value. So the calculated value is 2.42, whereas the tabulated value is 2.342. So if you are wondering how we have calculated this is, I simply told you in value of intercept in the slope minus the threshold value, which is 0 here, so that's why we haven't written anything, and then divided by the standard error. So you can easily see from the question that the standard error of intercept is 0.3001 and the value of intercept is 0.7264. So we have simply divided these two values to obtain the t value, which is 2.42, and you can see that this is not greater than 2.342, neither is it less than minus 2.342. So that means that it has little economic meanings. That means that it is significant. Now what does that mean that it is significant? It is simple as saying that we reject H0. Rejection of H0 means that this 2.42, it should be either greater than this or it should be either less than minus of this. So you can see that 2.42 is greater than 2.342, therefore we reject H0. So saying that we reject H0 is same as saying that the result is statistically significant. Now to comment whether this is a economic, in a practical sense or in economic sense, is it something significant? Well, if you look back at the equation, the value of intercept is 0.73. What does that mean? Even if the portfolio performance is 0, that is RMT becomes 0, even then that the stock return is equal to 0.7264. That doesn't make a lot of sense. It simply means that even if the market portfolio has 0 return, is it possible that the portfolio is not giving you any return, still one of the security in the same portfolio is giving you a return of 0.73? That is practically not possible. So that is why we are saying that the intercept here is practically not a useful value, and which is quite frequent. As I said that we focus only on the slope coefficient rather than the intercept. Okay, so what are my expectations, especially if you are preparing from an examination point of view, and that you should know how to use the T table if you have that in printed form, or if you are taking an online exam, you must know how to use the online T calculator that I have just discussed, so that you can decide whether to reject the null hypothesis or not. So next we are going to discuss data given in table 2.9. For this data, I have shared this for my NAS student. I have shared this on MS Team. For the general viewers, you can write me an email and I can share this data set with you, or you can simply download the book and go to chapter 2, and in table 2.29 you have all this data. So we have data on mean SAT scores of college students, and this is just a screenshot of that file, that is the table 2.9. So the reason why I was discussing this, we have a question here that is using that SAT data. So let's say we have the SAT data, SAT scores, and we want to see whether we can predict the average male match score on the basis of average female match score. So we have to run this regression, and then from the estimated residual we have to see whether the normality assumption is met or not, and then we have to test the hypothesis that the slope is equal to 1 or not. So how to estimate this equation, and that is so simple. I've already told you how to run regression in Excel. So just a moment, I need to open the file which has the table 2.29. You have to wait a bit, pardon for this. Okay, so this is the data, table 2.9. Our dependent variable is the male match score and the independent variable is the female match score. So we have this entire data sheet in front of us. So what we are going to do, we are going to use these two columns, the match score of male and female, and we calculate the slope and intercept. So you know that in regression, if we use the slope function, we can easily calculate the value of slope and the intercept. So we have the value of slope, we have the value of intercept. Now we can easily calculate y hat, which is equal to intercept plus slope times x. If we have y hat, then we can easily calculate residual, which is the difference between actual y and predicted y. So now we have the residual scores. If we have the residual scores, then by following the instructions in video number 9, you can easily make a normal probability plot of these residuals. And based on those residuals, you can, based on that plot, you can decide whether the data is normal or not. So in part A, we were to write the regression equation, which is simply intercept plus slope times the x variable plus the residual term. So this is the model that we can estimate using the given data. Now if we have to take the normality assumption, refer back to the video on normal probability plot, which is the video number 9 in this playlist. So in this video you can go and verify that the normal probability plot for the residuals of this regression is as follows. So now what you have to comment using on the pattern in this plot, if the normal probability plot shows a pattern which is close to a straight line, then you can safely say that the residuals are normally distributed. So if you have a look at this diagram, you can see that apart from a couple of data points, most of the data seems to be close to a straight line. So we can say that the residuals are approximately normally distributed, right? Now the part C was that you have to test the hypothesis that slope is equal to 1 or not. So how we are going to test, I have already taught you how to calculate the T calculated, how to find the value of T tabulated, and you can easily decide whether to accept or reject. So I am not discussing that again because that's already covered in the video. So then we reach to the end of this video lecture. So we have covered the complete chapter number 5 of Gujarati and Porter book. Thank you for watching, and I really appreciate the fact that it's a long video and you have invested a lot of time. So thank you for watching. Thank you for supporting the channel. Keep watching other videos, keep learning from the different playlists. Once again, Dr. Aisha Nazuk here. I'm interested to develop professional connections, so you can reach me out. We can work on, we can develop a professional connection. So thank you for watching. See you in our next video.